Welcome everyone to our ATAR Notes General Maths 3-4 Unit 3 Head Start lecture. This is part of our January lecture series and my name's Josh. And for the next 2 hours, we're going to be going through a fair bit of Unit 3 Head Start. I'll go through the specifics of that, but most of what we will cover will be Area Study 1. We won't cover any of finance, so Area Study 2, and we won't cover all of Area Study 1 just because Area Study 1 is so big. It makes up double what finance does in Unit 3, but essentially what it makes up is about 66% of it. So we're going to go through about 50% of Unit 3 if we think of it like that. Just a couple of things to start off. I'd just like to welcome you all to our ATAR Notes lecture series. So ATAR Notes has been around for a very long time, since about 2007, and they provide free resources, as well as some new paid resources to students who go through VCE, HSC. They even now operate in WA and Queensland. So it's really expanding from what it was really just doing VCE about 10, 15 years ago. So we offer all of these services, such as you can see here, student notes, lectures, discussion videos, and all of those sort of things. And now just to also point out, if you notice that I'm looking to my right, left, whatever it is on your screen, that's because I have my slides up on a monitor. So I'm not looking away from you. My camera is here, my monitor is there. That is why. But also what's really cool is we've started this new program. So we used to have a thing called Ed Unlimited. You've probably heard of that before. And we also have TuteSmart, which is our paid tutoring program, but we now have ATAR Notes Plus, which is essentially a subscription-based program in which we cover lots of new content, and we have all our ATAR Notes books, which are still available as hard copies. So we have our books, we have our topic tests and our course notes, all available on an online platform, as well as now an AI chatbot, which is really, really useful. It's learned from all of our ATAR Notes books, and it can answer really complex questions in terms of VCE. And we also now have flashcards, and there's also some questions and so forth on there, and other resources such as exams and so forth. So moving forward, just some general housekeeping. Please utilize the chat for those of you who are here at the sort of live premiere. Please utilize the chat. I will be there for the whole 2 hours, and I will be able to answer any of your questions during that time. After that, the chat will still be available, and this recording will be available for, I believe, about a week or 2 weeks. And then what it will do is it will go on to ATAR Notes Plus. In that time, please feel free to ask any questions. The chat will still be available afterwards just to look at. You won't be able to ask anything. I won't be available to answer anything, but you can look through and see if your question's already been asked. And as it says there, the lecture will be available afterwards. So what we're going to cover today. Is we're going to cover just some overview and study tips, because it's really important with general. I will call it further at times. I do apologize. When I went through this topic, it was called further. It's now called general. There are a couple of things that are really important for how you should go about studying for this subject. It is slightly different to other subjects such as, your maths methods or your English or your sciences or your humanities subjects. It is slightly different in terms of how I would approach it, and I'll sort of discuss that there. Then we're going to go through univariate and bivariate data. I'm going to go through a little bit of the application. We're not going to go into sort of our seasonalization, if anyone knows what that is. If you don't worry, you will cover that later on in the topic, but we won't go through that side of things. And then a little bit about who I am. So obviously my name is Josh. I've now been tutoring this is going into my 6th year of tutoring, which is a long time. It will probably be my last. I'm in my final year of medical school. So I've done 4 years of medical school plus a year of honours, and now I'm going into my final and 5th year of medical school at Monash University. I have 2 very adorable pets at home. I'm not originally from Melbourne. I have a dog called Maya, and I have a very chubby cat called Bella, and they are the things that motivate me to get through everything every day. So let's go through some course overview and some tips. So just some structure of general maths. I think what's really important is that although this is now going into your 2nd year of general maths in the new study design, most of you, or I'm assuming a fair proportion of you, probably have either older siblings or an older family friend or just an older friend who's given you some resources, or your teacher's given out some older resources from students in the past. There are subtle changes to this study design, and they have changed in the last 24 months, essentially. So last year was the 1st year, this year is our 2nd year. Essentially what changed was we used to have these 4 modules. Now what happens is that we only have 2 modules. So you didn't do 4 modules, your school chose 2 of them. Now, essentially, VCE or VCAR is choosing 2 for you. You don't get a choice. So you have 4 topics overall. Now, you have data analysis, which is the first one. It is worth double all of the other ones. So it is worth, think of it as worth 40% of the content. Each of the others is worth 20% of the content. All of that makes up to your 100%. So you've got data analysis first, which is easily your biggest. You've got finance, which is arguably the most difficult, and it'll be covered in the autumn lecture series. Then you've got matrices and you've got networks. And these are really important that you understand that these are the 4 topics that you need to know. Now, also as an extra point to that is that there are subtle changes. They're very subtle. The subjects did not change drastically, but there are subtle changes to each subject. There are some things that were removed, some things that were added. So really important that you, if you are using older notes, you are prepared to understand that some of the stuff you will look at will be relevant. Some of the stuff you look at will not be relevant. And then you have 2 exams for this. So really important, there are 2 exams. The 2 exams consist of a multiple choice exam and a short answer exam. Both go for an hour and a half. The multiple choice is worth 40 marks, 40 multiple choice. Short answer is worth 60 marks. There is X amount of questions. It can vary, but it's worth 60 marks in total. So you make up to 100 marks in total. So also really important, the study design, it changed in 2023. So really important that you are on top of that and that you read through it and that you do utilize this new study design. It's really important that you have this study design somewhere on your computer so that you can access it and you can read through it when you need to and when you need to decipher what is relevant and what is not. So a couple of things, what changed last year, just to solidify what has changed. So there was no more modules choice, which you've already discussed. There was removal of non-causation effect and population statistics. So if you see things about population statistics and you're a bit confused what's going on, don't worry, that's been removed. There was removal of simultaneous equations in matrices. Again, we're not going to cover that today, but that was a massive part of matrices. So you'll find whenever you do older exams and you do matrices that there's a fair amount of effort put into simultaneous equations and representation of linear lines, and you'll be like, oh, I have no idea what's going on. Don't worry, it's been removed, but it was super high yield content in the past, so it will commonly come up in old practice exams that you do. There was the addition of the Leslie matrix, so this sort of made up for what they removed from matrices. The Leslie matrix, it'll be covered in a later lecture, but you won't find practice questions on it past last year. And then there was a name change. Now, there was a couple of little things added into data, but they were only very subtle or just changing of wording, and so therefore I haven't really put in this slide. We'll cover it today, so don't worry about that. Just a couple of other little tips. Your calculator, really, really important. Please get used to using the correct calculator. Please do not use the Casio or the TN Inspire, so your white Casio or your black TN Inspire please do use those. Sorry, other way around, I'm thinking about science. Please do get used to using those. You don't have access to your little one. So I know a lot of you, which is why I get confused, I do apologize for that. You will find that sometimes in sciences, which is, I mainly do chemistry, that's why I was thinking that other way, you only use that little one. And a lot of people get really used to it, and that's just what they like to use. You don't get that in the exam. You only get your TN Inspire, and you only get your Casio class pad. Please get used to using it. You get it in both exams, you get it in all SACs. It's really important that you understand how to utilize it because it's going to be your savior at the end of the day. You may not use it for every question. I hope you don't use it for every question, but there will be questions where it will be far more useful and it will save lots of time. It will be your best friend. So always have some shortcuts on your menu screen if you can. If you can't, make sure you've got some little points in your summary book or your bound reference, whichever one you want to call. Please have some little menu sort of shortcuts in there, because if you sort of get into the exam and you stumble and you might have a mind blank, you just want to have those shortcuts in there so that you know where you're going and what to do. It is your best friend. Also from there, I sort of preface this with a little bit of a asterisk. I do say complete all the textbooks exercises, even if your teacher says, leave some behind. I preface this with a little asterisk. Do not do this as practice for an exam. This is the stuff that you do when you are learning the content. So as you go through, you're more than likely going to get questions from your teacher, or you're going to get some textbook questions, and they'll say, do these ones. That's your homework. I need to see that to tick it off and say that you're going well. I would expect you to try and do all of it on the basis that when you are learning it, the more you do, the better. When you are doing practice for the exam, so at the end of the year and you're going for your exam and you're pushing through, please, please, please do not use textbook questions. Why is that? Textbook questions are useless at the end of the year. So I'm going to get my little laser pointer out because I think it's going to be more useful. Textbook questions at the end of the year are useless. Why is that? Because textbook questions are broken into sections. So they're in sections. It's a section on univariate data, dot plots, or bivariate data using your manipulation circle to linearize data. You know what the topic is. You don't have to read a question and then decipher what I need to do. That is a really important skill, and that is one of the hardest things in the exam, is reading a long question and deciphering what I actually have to do. You don't do that in a textbook. The textbook sections tell you what to do. As such, please do not do textbook questions as exam study, but whilst you're learning the topic, it's really useful because they sort of hone you in on every little variation that the questions can have. And then when you go and do practice SACs, you then sort of have to decipher when I need to use those little skills. So great for that first grasping. I always think as well that you need to review sections. So especially with data. Data is worth so much, data, whichever one you want to say. It's worth so much, and you do it at the start of the year. And then a lot of students just forget about it. So they move forward and they go, all right, I'll come back to that at the end of the year. And then they forget it all. Always review sections, especially if there's an area in data that you're really weak at and maybe you do the SAC and you struggle with it and you get the question wrong. Go back and review that section after the SAC. Go back and review it a couple of weeks after the SAC. Go and review it a couple of months after the SAC. Always keep on top of it. So always keep refreshing yourself on it. And don't be scared to cut things out of your textbooks. You don't need to sell at the end of the year. Oh, whoop-de-doo, I'm going to miss out on my $20 or $30 from selling my textbook at the end of the year. Not a big deal. At the end of the day, if you want to cut things out of your textbook, feel free to do it. If not, you can also, photocopy. You're welcome to do that. But it's a really useful thing to do and to put into your summary book or your bound reference. You can also use sort of external ones as well. I do obviously suggest the ATAR notes. They're really, really good. And they're produced by students. So the questions are aimed at you. They know how they ask the questions. So they ask you the questions in that sort of way. Sometimes textbooks don't do that. And that's why I suggest not using them for exam study. And then summary book. Look, there are two sort of main ways you can do a summary book. I'm not going to go through it in super detail, but think of it as doing a really big summary book versus doing a really small summary book. Now, why I say there's maybe three is that you can sort of do a big summary book with a little summary book at the end. And what that means is you do your main summary book throughout the year. And then as you get close to the end of the year, you sort of summarize each topic in 2 pages, literally 2 pages. I'm not saying 4, I'm not saying either side of it, like, 4, 1, that side of the paper, that side, and then that side and that side. No, I'm saying a fold out, just those 2 pages. That is all you are going to summarize the entire topic in. So you're going to have 4 fold outs. You're going to have 1 for data, you're going to have the next one, you're going to have finance, you're going to have the next one, you're going to have matrices, you're going to have the next one, you're going to have networks. Now, you might say to me, well, the data's worth double. Well, I actually think as much as it's worth double, you can actually summarize data pretty well. There's a lot of jargon in data that you can leave to your big summary book. But nonetheless, there are 2 ways of doing it. You can make a really, really big one. These can be a bit of a pain to look through in a SAC or exam, but they do have everything. And if you're someone who really needs that extra support in your SACs and your exams, feel free to make it as big as you want. Now, secondly, there's also the far smaller one. It's a couple of pages. First of all, it says, you can print it off from a summary sheet. Try not to print something off. Please try and make one yourself. Yes, the positives are that it's a lot smaller and it's really quick and you can sort of go through it and you have some practice questions there. It's also really important to understand that it may not have everything if it's really small. And so therefore you may get to the exam and you may go, ooh, not really too sure where to find that. I didn't put that in there because I want to keep it really summarized. So there are positives and negatives to it, but having a small one is not a bad thing. Sometimes people really like those smaller summaries, and that's why you can sort of get the best of both worlds if you do that extra little bit. But the golden rule is you need to create your own summary book. That's rule number one. You cannot get around that rule. You have to cover that rule. So they are all my tips and tricks. My other sort of tip that I sort of left out in here is when to sort of start looking at exams. It's kind of cool with general that you can start looking at exams pretty early. And what I mean by that is the exams are distinctly broken up into sections. It's not like a science exam where all the questions are mixed in together and topics overlap. It's not like the methods exam where there's, everything is sort of interlinked. You sort of learn one bit and then you build on it with the next topic and you build on it with the next topic. So essentially all the topics are just one topic. It's not like your PE. It's the same thing as sort of like science and your humanities. They're all very similar in terms of they sort of build on top of each other. With general, they break it up into distinct sections. There is a distinct data section. There is a distinct finance section. There is a distinct matrices section. There is a distinct network section. These are broken up individually and they have their own little spots. As such, you can therefore start doing exams and just do the sections that are relevant as soon as you've done one topic. Now, I don't suggest that. I suggest starting exams once you've finished Unit 3. And what that means is you've done finance and you've done data. Sorry, you've done those two. Once you've done those two, you can start doing some exams. Yes, don't do the newer VCAR ones. I would even suggest sort of steering clear of VCAR, maybe do like a couple of really old ones. But beyond that, you should really be studying exams once you've done Unit 3. And you just do the half of the exam that's relevant. You just do data and you just do the finance. You don't do any of the matrices and stuff. You haven't done that yet. You haven't covered it in class. There's no point. But then once you've done matrices or networks, whichever one you do first, you then go, all right, I'm going to add that in. And so now I'm going to do that one next. And now you've done those, you're doing 3. So you're doing, 3/4 of your exam, a little bit more. And then once you've added the last one, you're already smashing through practice exams and you just add in networks or matrices, whichever one you did last. So let's jump in to Area Study 1, data. So we're going to start off with univariate data. A lot of this is going to feel like revision. A lot of this is going to feel mundane. The reality is it is. A lot of this content is quite mundane and you're going to be sitting here like, oh, same thing over and over again. Reality is it is. The summary book for this section, the big part of the summary book, not the little part, is going to be really large. And then you can condense it down really well. Because there's a lot of stuff here that's like, I don't really need it in my summary book. I'm going to put it there just because I want to have it there. But I don't really, in my little summary, I don't need it because it's stuff that, I should know pretty well. So, jumping in. We start off with data. So, what is data? So data is all about facts and statistics that are collected together, in the reference or analysis. And then we have variables. So what we measure to collect data. So what variables do we look at? What do we do to collect data? And how many variables? So we then look at univariate 1 versus bivariate 2. And this is where things get a little bit more complicated. So as you can see here, we then can discuss, well, if we have univariate and we have bivariate, what if I have, I have 2 pieces of data, but what if they're both different? Well, then I can say, well, one of them might be categorical, which is names, and then one of them might be numerical, which is, your values and your measurements. So from there, what else can we get? Well, we can get from here different subtypes. So we have categorical and we have numerical. Now, we can break these down further, as I said, into our subtypes. So we'll start with categorical. So categorical is all about categories. Makes sense? It's called categorical. It's got categories. Now, the categories that we're going to look at, are we going to look at things like eye color, football team, etc. Now, what's really cool about those things is you can't really order them. Like, sure, maybe like a football team, you can order it by the ladder, but you can't really order it. There's no way of ordering these things. But there are ways of ordering other categories. So order is our way of subcategorizing categorical things. So we have nominal, which is, there's no sensible way to sort these categories. So if I'm doing eye color, it doesn't really matter the order of it. I can do brown eyes first, I can do blue eyes first, I can do green eyes first, I can do aqua eyes first, I can do hazel eyes first. It doesn't really matter which order I put these in. So I go, in this case, I do hair color. I've got, blonde, brown, red, black, etc. There's no way of ordering that. However, if I do ordinal categorical, this is a little bit different. I can order some categorical pieces of data, such as very satisfied, somewhat satisfied, neutral, somewhat dissatisfied, very dissatisfied. That has a general order to it. Yes, you could start at dissatisfied or satisfied. Doesn't really matter which way you start, but it has a general order to it. Now, numerical data, on the other hand, can be measured. So categorical data cannot be measured. It needs to be sort of counted. It doesn't even need to be counted, it just needs to be obtained. Numerical data, in a sense, is measured or counted. And we think of it in two distinct ways. There is discrete, and then there is our continuous. Now, what is the difference between the two? Well, discrete is more in the sense of something that we count, and therefore it's usually whole numbers. Now, there are exceptions that allow some decimals in there, but it's more about counting. I can't say I have half a dog. If I'm going to count the number of dogs people have, or the number of pets people have, I can't say I have 2.5 pets. That makes no sense. It needs to be 2 or it needs to be 3. There is a distinct number. Now, there are some exceptions to that. Things that are counted in 0.5s, or maybe like a common example in the past has been an ATAR. So ATARs go up by 0.05s. That is a discrete because you can only be on a 0.05. It goes, 0.05, 0.10, 0.15, 0.2. That's how it goes up. Like 99.95, 99.9, 99.85, 99.8. Like it counts by that. Usually, though, we say it needs to be a whole number. Continuous, on the other hand, is something that is more measured. And it's something that usually they use weight, temperature, height. These things can go to as many decimal places as you want. Depends on how accurate you want to be. So if I weigh, 5 people and I find they're, 80.2, I find one of them's like 100.5, I find someone's like 89.32, I find someone that is like 92.67, or I find someone that's like 50.25. It's a measurement. They're different values. They can be anything. They don't have to fit into, 1, 2, 3. They don't have to fit into that. So that is how we look at it. And this is a great way of sort of summarizing it in your summary book. You have, your categorical, numerical, and then you go, all right, well, is there an order? Is there not an order? Do I count or do I measure? And that is how we look at these things. So another way of thinking about it as well is these questions that I'll pose to you. So my first question is, can it be manipulated? So can I manipulate this piece of data? Does it make sense to find the mean, median, mode, range, etc.? Yes, well then it's numerical. If it's not, then it's, it's categorical. It makes sense to subtract 2 heights from each other. It makes sense to find the median height, the mean height, etc. It doesn't make sense to find the mean, football team. That doesn't make sense. There's no order to it. There's not even anything else going on with it, so you can't really do that. Can it be counted or measured? Yes, no. Although numbers usually mean that a variable is numerical, it always doesn't. This is a really good point. A really common categorical ordinal, so it can have an order, a categorical ordinal piece of data. It's really common and comes up a lot. Postcodes. Postcodes are a number, so you would think that's numerical. However, postcodes describe an area. So my postcode describes my area. So, etc. Example, 3000 is Melbourne CBD. 2000 is Sydney CBD. They describe an area. They are not describing a value. Yes, they can be ordered because you can start at 1 and you can go to whatever the largest one is, but they describe an area. And as such, that postcode is describing a categorical piece of information. It's a categorical ordinal piece of information. So this is that example there. Is the number being used as a name? So postcode. Another way of thinking of this is a house number. Another way of thinking of this is like a rating, so 5 stars. A really common one as well is like shoe size. So shoe size, that comes in numbers. Starts at 0, goes up to ginormous sizes. That's just like 20 or something. they are a number, but they are utilized to describe a size. So they're utilized to describe a size, and therefore we would call that ordinal categorical. So here's a really quick question for you. If you're playing along at home, pause your video now just quickly and go through and name each of these. So I'd go through the first one and say, all right, how often do you study? Often, sometimes, rarely. Well, if I said, how much did I study in hours? I think that's sort of like a category. I think that's like a numerical. Could be continuous if they're asking for specifics, but it could also be discrete if they're just asking to the hour. But they're actually asking it in terms of often, sometimes, rarely. Therefore, I'm thinking this is categorical, and that does have an order. So I'm thinking categorical, ordinal, etc. Go to the next one, temperature in degrees Celsius. Well, this is a measurement, so I'm going to say this is numerical continuous, etc. Move on. I want you to go through and do the rest of them. So pause, 3, 2, 1. And hopefully you've unpaused and you're back. Hopefully you had a go at this one and you got the answers here. So another one here, this is from the 2016 Further Exam 1, so a multiple choice exam. We have the variables of blood pressure and age are which of the following? So what's really cool about this question, or what was not very cool about this question, was only 31% of people got this right. So this was more of a difficult question. So have a quick think. 3, 2, 1. All right. So this question here was a little bit more difficult in terms of that we find that there are two variables, and one of them is very much sort of a categorical ordinal, because as you can see here, we've been told that low, normal, high. It's clearly categorical. It's clearly describing what's going on, and a low, medium, high. Now, then we have under 50 and over 50. Now, what was really interesting about this question is a fair proportion of people thought this might have been a numerical piece of data. So they thought this could have been a continuous piece of data. And so a lot of people went for E. And then a lot of people also went for D, because we had an ordinal. So we clearly had an ordinal. So that's covered with our low, normal, high. But a lot of people said, oh, well, under and over 50, it's just two categories. So we're just going to say this is nominal. Well, it actually wasn't. It's also ordinal, because you can order that. You can say, well, if you're under 50, that's at the start. If you're over 50, that's at the end. You can order that. So the answer to this was actually B. So both ordinal variables, and only 31% of people got this right. That's 31% of the cohort got this question right, which was question 2 on the exam. So usually you will find, it's something I didn't talk about in the tips, with the exams, the easier questions are at the start, the harder questions are at the end of the groupings. So you'll have, your 16 data questions and you have 8 of all the others. And usually the first 2 questions will be easier, and usually the last 2 or 3 questions will be a lot harder. The middle questions usually vary, but it just happens to be that the first 2 questions are a little bit more straightforward than the last 2 or 3 questions. It always happens to be that way. This is essentially one of their more straightforward questions on the exam, and 31% of people got this right. So if you're able to get your head around this concept and understand it, you're already going to push yourself ahead of it at a minimum 50% of the cohort, and that's what you really want to be doing. So now that we've looked at that, let's move into univariate data. So univariate means one variable. So uni means one, and it can the only one thing changes or is manipulated. So as such, you say, what's your favorite color? And then you just count the number of people. So this would be sort of a numerical discrete sort of piece of information, or actually it probably wouldn't be, because you've got a category here. So you're probably looking at categorical. You're actually looking at categorical data here. So what you can see is your variable is actually in the left column, and so you're looking at categorical data here. And then you have bivariate data, which we'll cover in a bit, but essentially bivariate data is 2 variables, bi meaning 2. There are 2 things that change or can be manipulated, and these 2 things can change or be manipulated in different ways. You might actually have numerical versus categorical data, or you might have 2 pieces of categorical data like you've got here. So you've got a year level, so categorical ordinal, because it can be ordered, and you've got categorical nominal, which is your non sort of way of manipulating it, because your non sort of ordering way, because there's no way of ordering this piece of data here. So bivariate data is super interesting. More on this later. So let's start off with what type of graph do we use. So this is a really good little summary to go in the smaller side of the summary book. So a really good summary to say, all right, if I've got categorical numerical data, it's going to go in one of these three types of graphs or tables. Now, if I actually have numerical data, that is, as you can see here, one of those 1, 2, 3, 4, 5 graphs or tables can be utilized to display numerical univariate data. So below you can see here, you've got a frequency table. So frequency tables are really interesting because they're just the raw data shown to you in the easiest way they can. So raw data is data that has been manipulated, it's just obtained, and it's just what they had on their sheet. You're generally going to obtain your data for something like this in a frequency table. So it's the easiest and most simple way of displaying it. Usually you don't want it displayed in a frequency table. The only way a frequency table can get a little bit more complex is if you put a percentage in it. So a percentage frequency table is essentially when you get the whole cohort and you find out what percentage each one was, and it should total out to 100%. Now you can add this as an extra column, or you can just make it separate like this one here. The most common way of displaying categorical univariate data is through a bar chart. Now, a bar chart is distinctly different to a histogram, and we will discuss that when we get to our histograms. But it's really important to understand that categorical data has this sort of broken up approach. Because the categories, order or not, are separate, they don't sort of follow along by numbers. We need to break them apart. We need to have gaps between our bars. So in a bar chart, there is a gap between each bar. Also in a bar chart, we usually try and keep it as one color. So we usually try and keep each of the bars the same color, they're the same width, and they're the same distance apart from each other. The only difference is their height, which is obviously their frequency, because on the y-axis you've got your frequency, and on the x-axis you've got your categories, so your type of pet, or etc., or whatever it is. As you can see here, pets at home, and you go, all right, I've got cats, dogs, birds, fish, etc., and you then do your frequency on your y-axis. So categorical data is also really interesting because it can be described in a really sort of succinct and straightforward way. So there's a template that I want you to use in your summary book as to how you're going to answer all categorical numerical data questions where they want you to explain it. They want you to write a paragraph. They want you to say, hey, what actually does that graph show you? What is that graph telling you about what's going on? So you must essentially summarize the context of the data. That's always the first thing that I think you should do. You should always summarize what is going on in your data. So give some context. What is it? What are we actually measuring? Or what are we counting? What are we taking the frequency of? What's going on? So obviously you won't be measuring and counting to use categorical, but nonetheless, you're saying, all right, I'm getting the frequency of the number of the type of pets people have in my class. You want to identify the mode, so usually what's the most dominant category, and then quote its frequency, and then quote other frequencies of interest. So let's have a look at this question here. I want you to comment on the data shown in the frequency table below. So if you want to have a go at this, please feel free. I'll pause it here, or you can pause it here. So pause here and take a good 30 seconds or so, maybe a little bit more, maybe like a minute, and write out an answer that gives all 3 or 4 of those points: context, what is the most dominant category, what is its frequency, what is some other points of interest. So here we've got, right, so 3, 2, 1, pause. Right, hopefully you're back. So here we've got 3 climates: hot, mild, cold. We've given the frequency, we've given the percentage frequency. So we'll start off with, this is what our answer looks like, but how do we break this down? Well, first of all, we had context. The climate types of 23 countries were classified as being hot, mild, or cold. So we've given context. There were 23 countries that were surveyed in this sense. We weren't given the context that they were in the question. You weren't given the context that these were countries, so if you didn't mention countries, that's okay. But obviously in this question, we were talking about countries. And we wanted to classify them as being hot, mild, or cold, mild, hot, whichever way you want to talk about it. It doesn't really matter. Nonetheless, that's a good way of sort of looking at it. Then we say the majority of countries, 60.8%, were found to have a mild climate. Now, really important, Percentage frequency dominates standard frequency. So please use percentage frequency if it is available. If it is not available, you can use your common frequency, but I always suggest using percentage frequency over common frequency because it's already been manipulated. It's a better piece of data. It's a better piece of information. We like it more. It gives and provides more information. So therefore, I always say, you know what, if it's there, utilize it. And then we've got our other pieces of information. So note other frequencies. So of the remaining countries, 26.1% were found to have a hot climate, while 13% were found to have a cold climate. So it's just commented on the other frequencies. Now, this table might have been much larger. There might have been, 8 categories or something. If it's much larger, you don't need to comment on every single one, just ones of note. You could say the least common climate was cold with 13%, or the next most common climate was mild, or hot, sorry, with 26.1%. So you just give what is the next, what is the least, or just something that's interesting. You don't want to say every single thing. In this here, you can because there's not a lot of information, but you don't want to go out there and just write every single thing down on the page. So then we move into numerical. So numerical, also really interesting. You can also display numerical data in a frequency table. Again, this is your last resort. You don't really want to be doing this. So it's sort of the last resort as such. And you can sort of put it into a frequency table. You can also sort of range it. So in this case here, you can use ranges. Think of this as like intervals. You're also welcome to utilize this with tables. But again, last resort, we'd rather use like a dot plot. So if we look at this here, we go, all right, dot plots used for discrete numerical data. Only the x-axis is used, so we don't have a y-axis. And the number of dots represents the frequency. So essentially, we have pieces of information that are on 1, 2, 3, 4, 5. Sorry, that's sort of been squished down. Didn't really hold its position well. But as you can see here, we have 4 on 1, we have 2 on 2, we have 1 on 3, etc. So what we're looking at with the dot plot is just, we're looking at sort of how many pieces of information are each one. We can then sort of find a mean, a median, or a mode, etc. This would really be used for this numerical discrete rather than numerical continuous. Numerical continuous is probably not all that useful on this one here. You can find the mean. You can do that by counting the dots and then finding the middle value. So if I go here, I've already got it up on my page, but if I go 1, 2, 3, 4 in our first one, I've got 2 in my second one, that's 6. I've got 7, I've got 8, 9, I've got 10, 11. Well, my middle point is going to be my 6th point because there's 5 on either side. 1, 2, 3, 4, 5, and then 6, and then, pardon me, and then 7, 8, 9, 10, 11. So there's my 2 points of 10. So having my 2 points of 10, I'm therefore going to have my middle point being 6. As you can see here, I've got 4, and then if I'm counting down, I can say 1 and then 2. That's my 6th point. If I'm counting up, you're welcome to do the top one. Doesn't really matter. Both going to end up being 2. You've got your median value. And then you've got your stem and leaf plots. Now, stem and leaf plots can be utilized for continuous. Once again, probably still not all that useful, but you can use continuous data on it. Probably the more useful way, we'll talk about it in a bit, but it's more useful here to do numerical discrete again. Now, you've got a stem. So essentially here we're saying that our stem represents 40, so 4, and then whatever goes behind it is the 1. So this example here would be 41. So your stem is the first digit, your leaf is the last digits. Same with the stem, it can be more than 1. So example, as you can see, it's like 40 and then 1. You always need to include a key here because in this case here, what if the 4 was representing 400 and then the 1 was representing the 10s? So it could be 410. Really important that you do that because in most cases, if you don't have a legend, you cannot utilize a stem and leaf plot, and your answer will be wrong if you draw a stem and leaf plot but don't give a legend or a key. As you can see here, you got your stem 1, 2, 3, 4, 5, 6, and you've been told in your key that if it's 1 and then 0, it's 10. So if it's 2 and then 0, it's 20. If it's 3 and then 5, it's 35, something like that. So you can see here in your stem and leaf plot, you've got a whole bunch of values. They've been ordered. And as you can see, this answer is 10. But if I said, oh, what if this was 100? Well, then I'd have to make this 100. So it's really important that you know how to utilize that, you know how to apply that distinct methodology of utilizing a stem and leaf plot. It is a little bit difficult. So really important, a leaf plot has to be ordered, and you can split a stem and leaf plot. Now what I mean by that is, so let's just use 2 here for example. So you can see our 2 on our screen. We have a bit of information, we have 4. Now what if I wanted to break that down and say, all right, I want 2 categories. Well then I'd go, 1, 2, and then 2 again. Now the first 2 category, you go 0 to 4. The second 2 category, you go 5 to 9. Now you're welcome to do that. If you do that, you need to do it for all of them. So for example, in our 4 one, as much as there's only 3 things there, you'd have to do 2 4s. You go 4 and you'd have your 2 4s next to that. You go 4 again and you do your 7. Same as 6, you do 6 and you go 0, 1, and then you do another 6 below it and you do the 9. So you are welcome to do that when you have lots of information. Breaking down a stem and leaf plot into doubles is really, really useful, but only do it if it's, you've got like 6 or 7 pieces of information in each one. I think if it's less than that, like this one here, it works as is. I think once you get to like 6, 7, 8, then it's useful breaking it down. But before that, it's not that useful. I wouldn't bother doing it. It's not all that. It's not the best thing you can do. And it's not called a stem and leaf ploys. Sorry, it's a plot. Now, histograms. Now, this is where we talk more about a numerical discrete. And the best way to talk about this is usually putting things into categories. Not categories, intervals. Sorry, I shouldn't say categories, I should say intervals. Putting things into intervals. Now, the example I put on the screen doesn't have intervals. Once it pops up. No, it does have intervals, sorry. I did change this. The example we used to have didn't have intervals, and I was like, it annoyed me. So I've obviously gone and changed it. I did forget that I changed it. Intervals. So intervals are really, really useful because then all your continuous data, you're sort of sub-categorizing it in a sense, but it's still categorical data and using the raw data. So in this graph, you cannot find your mean or your mode. It's not that useful. You can find a median or a mode in terms of your intervals, but that's not useful. You get your raw data out and that's when you find your mean, your median, your mode. What you look at here, if you're able to describe this, is you look more at the shape. You look at the spread, you look at the center. So you say, all right, our central spot is between 5 and 9. So you don't talk about the exact median or the exact mean. You talk about your center spot. And then you talk about outliers. You might have a bit of outlier information. Like you might have a really big peak somewhere and it's not that useful. You talk about that as an outlier. So that's where histograms become more common for numerical continuous because then you sort of interval it. You put that information into intervals and you get the relevant information out. Now, numerical continuous data is most useful when it's bivariate. We'll talk about that a little bit later on, but that's because sort of our bivariate data just provides a little bit more oomph, if that makes sense. You get a little bit more ability to manipulate, you get a little bit more ability to work with it, and a little bit more ability to sort of just display it differently. And that ability really, really shows when you have continuous data. And continuous data is far more useful when it's bivariate. When it's univariate, it's not as useful. So this is where univariate data gets really tough. So univariate data as a whole is not all that difficult. This is where it gets quite difficult. And this is the point in this session, which if you haven't really been paying attention, that is fine. You should pay attention right now. This is where things get a little bit difficult. So sometimes we have a data range and it's too big. The most common example of this is if you look at the populations of the world. You look at somewhere like Samoa, and I think Samoa is somewhere around, 9,000, 10,000 people. Even like Vatican City. Vatican City, don't ask me how that is a country, but nonetheless, Vatican City is something like 300 people. It's really, really small. Same with somewhere like Samoa. Samoa has something like 9,000 or 10,000 people in it. So that's really small. But then you compare it with somewhere like China or India, which have over 1 billion people. You put them on the same histogram, and it just doesn't work. You're too far apart. You cannot work with that. Your histogram is going to take up more than one page because you're just spreading it out. Unless you do really big categories, and then that sort of skews it. It's not right. You're sort of manipulating it incorrectly. So in these cases, we use what is called a log scale histogram. And you might say, what the heck is that? A log scale works like this. So a normal scale goes, 0 to 10, 10 to 20, 20 to 30, 30 to 40. So you have 10 in between them. That's how a normal one works. So if I've got 10 in between them, I'm counting up. So we use pluses and minuses on a normal scale. We plus this much or we minus this much. A log scale works by multiplication or division. So 1 to 10, multiply by 10. 10 to 20, 10 to 100, we're multiplying by another 10. If I go 100 to 1,000, I'm multiplying by another 10. So a log scale puts things in categories of 1 to 10, 10 to 100, 100 to 1,000, 1,000 to 10,000. So the intervals are all different sizes. However, they are the same width apart. You're not making the intervals different widths apart. You're keeping them the same width apart, but what is in the interval is very distinctly different. The first interval is made up of 10 numbers. The next interval is made up of 90 numbers. The next interval is made up of 900. The next interval is made up of 9,000, etc. And so therefore, a log scale gives these numbers. So there are a few properties I want you to understand before I sort of describe that. If the raw piece of data is greater than 1, its log value is greater than 0. If a number is greater than 0, so the raw piece of data, so it's between 0 and it's between 1. So it's like 0.5 is the piece of data that you got. Its log value is actually negative. So you're going to get a negative log value. So your log value will be negative. Now you do this all on your calculator. If the number is 0, so they actually didn't have anything, so you're measuring and there was nothing, it's undefined, you're not going to be able to log that, don't worry. And for some reason you are measuring something that goes into negatives, maybe temperature. If the temperature is in its negatives, you actually cannot utilize logs. So there's no way of logging a negative number, it doesn't work. So therefore what we're saying is that if you're measuring temperatures and they're really, really far apart and you wanted to use log scales, but then you get a negative temperature, well, you're not going to actually be able to plot that piece of information on the log scale. So when displaying logs on an axis, we use their order of magnitude. So 10 to the 2 becomes 2, therefore we must label the axis as log variable. Now, this is what I mean by this. So essentially, and again, I didn't fix this one, I should have fixed this one, the histogram is wrong as well. These are intervals. Think of this interval as 0 to 1. So the first one here, as you can see on the screen, this is 0 to 1. So if I am between a log of 0 to 1, where am I? So remember we discussed on our last page that if the raw piece of data is greater than 1, then our log is greater than 0. Well, if I'm between 0 and 1, that means my raw data is between 1 and 10. So this is between 0 and 1 on a log. It's between 1 and 10 in my raw data. If I'm between, next category, we'll say this is between 1 and 2. So we'll say, all right, this is between 1 and 2. Now, being between 1 and 2, I say that my log is between 10 and 100. So my raw data is between 10 and 100. But I'm saying it's between a log of 1 and 2. Next one, I say, all right, it's between 2 and 3. Again, this got squished down. I do apologize for that. I don't know why a lot of the graphs it's because I changed the shape of the slides to fit the full screen and they got manipulated down. I do apologize. I should have edited that out. But let's just say the next one's between 2 and 3. So our next one here is between 2 and 3. Being between 2 and 3, we say that it is between 100 and 1,000. So any piece of information measured is between 1 and 1,000. And that's why we call this log and then whatever our variable is. So if we're talking about population, we'd say log bracket population. And as you can see here, this is what our log guide means. So your log is the value up here. It's this value that the 10 is to the power of. So a log of 2 is essentially 10 to the 2. And it is 100. A log of 3 is essentially 10 to the 3. 10 to the power of 3. 10 to the power of 3 is 1,000. A log of -1 is equal to 0.1. So if my interval is between a log value of -1 to 0, I'm between 0.1 and 1. Now, if I'm between a log value of 0 and 1, I'm between 1 and 10. So that is your guide. Now, how do I actually calculate logs? Like, what if I've got a value of, 245? Well, I've got a value of 245. Oh, maybe we'll use something. Shall I use something else? What about if I say I have a value of 150? I have a value of 150. Now, you might say to me, I think that is going to be 1.5. 1.5. I've got a log of, no, wait, that's 15. I'm going to say 150, sorry. I've got a log of 150. So you might say to me, being a log of 150, you could figure out where it's going to be, and you could say, it's going to be close to 2. Well, that's probably right. I was trying to think of probably a better way of saying it is, what if I thought of a log of, we'll go back here. I'm looking at a raw piece of data, and my raw piece of data is 5.5. So 5.5 is smack bang in the middle of 1 and 10, because there are 9 numbers between 1 and 10. The middle is 4.5, so I add 4.5 to 1, I get 5.5. So I'm at 5.5. My raw piece of data is 5.5. My raw piece of data being 5.5, being smack bang in the middle of 1 and 10, I would assume it would be smack bang in the middle of 0 and 1. What you'll find is it's actually not, because log scales go up very differently. They don't go up uniformly because of that multiplication, and therefore your actual log value might be more like, a 0.4 or a 0.6. It's not going to be 0.5. It's not going to be smack bang in the middle, even though the raw data is smack bang in the middle. Now, always use your calculator to calculate your log value. So if I want to find a log value, I've been given the raw data, and I say, all right, I've been given 150 as my raw data. I go log 10 of 150. Now, this will be in your calculator. You'll be able to find this in your calculator. There is a log in your keyboards for your Casio ClassPad, or if you're on your TN Inspire, there's actually just like a shift shortcut to one of the buttons, and you find that you'll get your log 10, and then it will give you brackets, and you just have to put the number in the brackets and press enter, and you get your answer. So as you can see here, your log 10 of 150 is 2.1, which if I go back, it makes sense. It's between 2 and 3. And also really important here is to identify how our log scale is working. 150 is only 50 of the 900. There's 900 raw pieces of data between 100 and 1000, and I'm only 50 in. I'd assume that I'm actually less than 10% in. So 10% of 900 is 90. So if I was going up uniformly, my log of 190 would be 2.1. And therefore my log of 150 would be less than 2.1. But my log of 150 is more than 2.1. That's because logs go up differently. They go up on sort of an exponential sort of way. They go up non-uniformly, and therefore your log values do not exactly match the exact position that your value is. Really important to understand. That's why you need to calculate it every time. So put it in the calculator. Now, what if I have a log number and I want to find what my actual value was? Well, if I'm given a log number, I just go 10 to the power of the log. So if I was given a log of 1.683, I go 10 by 1.683. And being a log of 1.683, I assume it's between 10 and 100, because I've got this scale here. Well, it's 1.683, and needs to be between these two pieces of raw data. It is. It's 48. It's perfect. It's perfectly been pulled out, and it's in between our 10 and our 100 because it's 48. Always use your calculator. This is a really good example to have in your summary book. Same with this one back here, having these two in your summary book next to each other, with then an example of a question such as this. This is a VCAR 2016 question. It was really poorly answered, like extremely poorly answered. I want you all to have a go at it. I know this is your first time seeing logs, so if you do struggle with it, that is okay. This is your first time seeing logs. I don't expect you all to be acing this straight off the bat, but I do want you to have a go at it. So as you can see here, we've got a histogram below that shows the distribution of number of billionaires per million people for the same 53 countries as question 6. Don't worry about the countries, it doesn't really matter. Based on this histogram, the number of countries with one or more billionaires per million people is. So this is the number of billionaires per million, and it's counted in each country. So they counted how many billionaires per million people there were in each country. And then for each country, they were like, all right, so there is 5 millionaires per person. All right, we'll do a log scale and we'll put it in. So it says here, the number of countries with one or more billionaires per million people is. So how many of these countries, how many of these people in this graph here display more than one billionaire per million people? So more than one. But remember, this is on a log scale. Really important. So, have I got this question? I will give you, I'll give you some time. Again, pause it. 3, 2, 1. Pause. And hopefully you're back. Now, if you're back and you're confused, I will explain a little bit more of it, then you'll be welcome to pause it again and have another go at it. But if not, we'll jump into it. So as you can see here, we have a log scale, and we want to know the raw number of people, or the raw frequency of more than one. So what is a log of 1? Well, the first thing I would do is I'd go to my summary book. So I'd go to my summary book and I'd go here. So hoping this clicks in. I'd go to here in my summary book and I'd go, all right, what is 1? Well, 1 in my summary book is 10 to the 0, which is a log number of 0. So if it's a log number of 0, I need to go to here. And a log number of 0 is here. I draw a line up here just to cut off everything to the left. I don't care about anything to the left. I only want the stuff that is on this right side here. So being on this right side, I look at the frequencies and I go, all right, well, between 0 and 1 means there is 1 to 10. So the number of billionaires per million people is somewhere between 1 and 10 for those countries. So there are 9 countries there because I go and I check it on my frequency, and my frequency is at 9. Go across, I get 9. So there are 9 countries that have more than one, between 1 or 10 billionaires per million people. And then I go here and I say, all right, there is one country here that has between 10 to 100 billionaires per million. So they could have, 40 billionaires per million people. These countries here could have, 5 billionaires per million people. So what's really important is that these are the two you need to add together. You get an answer of 10. One of the most common answers on this was 1, because people looked at it and went, oh, log, I don't really understand it. It's 1's here, so there's a frequency of 1 above it. So I'm going to say, all right, it's 1. Please, please, please do not answer a question like that. Please do not just jump into it and go, I'm really confused by logs. I'm just going to go with it. Try and have a go at this question. If you have that breakdown that I went to, that slide that I went to, you have something like that in your summary book with examples such as this. I know in this question this was less relevant, but having examples like this will make this distinctly easier. So really important you work through that. Now, let's move on from logs, because I don't want to spend this whole time on logs, but logs is one of the more difficult things that you will cover. Pushing through. Let's move on to the 5-figure summary. This is the next sort of difficult part of this. I think you'll be okay with this. I think most people cover this pretty well, but the first time you see it, you might be like, oh, that's a little bit more confusing. So, 5-figure summary. The 5-figure summary is made up of a minimum, the quartile 1, the median, the quartile 3, and the maximum value. Now, the best way of looking at this is on box plots, which we haven't been through yet, and this is why I kept it. We're going to go through box plots here. So, you can work this out in the calculator. If you are given all the data in a completely obscure way, it's not in order, you can just put that all into your calculator. Maybe given like 30 values in a SACRA exam and the values are not in order, just go through and put the values into calculator. You don't need to order them. You can just put them in a sheet, and then you can go through and do this all. You can go to your settings, you can go to your keyboard and go, all right, I want a 5-figure summary, and it'll come out. It'll give you a 5-figure summary. You can even make it order it for you, so you can order all that data, etc. So forth. But if I've got this data here and I say, all right, I want my 5-figure summary. Well, first of all, I'm going to say, all right, well, how many numbers do I have? I have 14 numbers. That's the most important thing. How many numbers do you have? Well, I have 14 numbers here. I've counted it out. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 numbers. So the median is going to be between the 7th and the 8th number. That means the median is going to be in the middle of those two. So I need to add those two together and find the average of the two, or the average between two numbers that are 1 apart. It's just going to be 0.5 between them. So as you can see here, I've got 7 on the left, I've got 7 on the right. Then I go, all right, what is my first quartile? Well, my first quartile is going to be the median of those first 7 numbers. And the median of those first 7 numbers is going to be the 4th number, because it'll be 3 on either side, so it'll be 8. Same with the back group, so the second 50%, I'm going to find my 4th number in there, which will be 21. As you can see there, I now have my Q1, I have my median, and I have my Q3. And then my min and my max is really easy. Well, my min is going to be my smallest number, and my max is going to be my biggest number. So if it's in order, I just go to the end, I go to the front, and I go to the end. Now you can do the same on a dot plot. We already talked about the median before, but you can do the exact same thing on a dot plot. You have this information, you can go ahead and do it. You can do it on a leaf plot. You can do it all the same. But the single best way to represent a 5-figure summary is through a box plot. So, first of all, you need to figure out what your IQR is. Now, you might be looking at me and saying, what's an IQR? You've just jumped from box plots to IQRs. Now, box plots display IQR really, really well. Now, IQR stands for interquartile range. The interquartile range is the range between your Q3 and your Q1. So, essentially with this, you can also do outlier calculations. Now, before I jump into outlier calculations, I want to show you what I mean by that. So, you've got a box plot here. Now, again, I think my axes have all gone a bit skewed when I made these slides bigger. I do apologize that these were not fixed up. But as you can see here, I've got my box plot here. Now, assuming this is spread out, we're going to 26 and we got 1. What you can see here is that your box plot represents a couple of things. It represents, first of all, each of your 25% ranges. So it represents your minimum, your maximum, your Q1, your median, and your Q3. Now, where does it represent that? It represents it at each of these points here. So the earliest point either being the fence, so the fence, oh, I lost my mouse, there it is. This fence here, or this minimum outlier or an outlier will be your minimum point. In this case here, we've got an outlier, so your outlier is your minimum point. Your Q1 is this first line of the box. Your median is the line in the middle of the box. Your Q3 is your line at the end of the box. Now, your maximum, again, works the same way as the minimum. It's either the fence, so the fence which is here, or if you've got an outlier, it's the outlier. So the outlier always takes precedence because that's higher up or lower down, but if there is no outlier, you utilize the fence. Now, as you can see here, these two are outliers, but I think this is the most important point, is your fences. So we're going to talk about fences in terms of outlier fences in a second, but these fences are different. You will draw this fence here at the largest and smallest. So at this end here, this will be the largest. So this is the largest, and this down here is the smallest. Now, the largest non-outlier value. Please do not draw your fence at your outlier calculation, which we'll discuss in 1 second. This fence goes, the one that I've got highlighted right now with my mouse, this goes now at your smallest non-outlier piece of information. Now, if you've got no outliers, this will be the minimum. If you have outliers, you use your next smallest piece of information. So in this case here, I know this scale is wrong, so we'll use the sort of little points. 1, 2, 3, 4. 4 right now is my smallest non-outlier piece of information. 1 is an outlier. So in this case here, 1 is an outlier. Now this may be very wrong, it's just an example, but 1 is an outlier. However, 4 is not an outlier. Now my fence, my outlier, fence might have been at 2. So I might have done a calculation and found that my outlier fence is 2. Therefore my outlier 1 is, well, my value of 1 was an outlier because it's less than 2. But I'm not drawing my fence at 2. I'm drawing my box fence at 4 because that is my smallest value that is not an outlier. Really important. At the other end, it's the same thing. So let's say this goes to 26. So I have an outlier at 26 and maybe my fence was at 24. Maybe I did my outlier calculation and I found that anything above 24 is an outlier. Therefore, 26 was an outlier. But then my next biggest value was 23. So I had a 23 and then I had a 26. Well, 23, therefore, is going to be my fence end because that's my largest value outside of my outliers. Now, how do I do this outlier calculation? The reason why this box plot is actually like slightly wrong is because even with the axis wrong, none of those values would have been outliers. Your outlier calculation looks like this. Your lower outlier fence, not the fence that you draw, your outlier fence is Q1, take away 1.5 by RQR, and your upper outlier fence is Q3 plus 1.5 times RQR. That is how you determine outliers. This is a formula you need to have in your summary book, and it's really important you utilize it whenever you draw out a box plot. Now, the other useful thing with box plots is it represents your 25-25. So, given that this is your minimum and this is your Q1, you know that 25% of the data is between that point there. Given this is Q1 and median, you know there's another 25% in here. Given this is the median and the Q3, you know there's another 25% in here. So then you can say, well, there's less than 75% of information below whatever value Q3 is. Or there is 75% of information above 5, because we know this is 5. So there was 1, 2, 3, 4, 5. So this line is at 5. So I know 75% of my data in this that this box plot represents is above 5. And then between Q3 and max, there's another 25%. So there's your 100% if you add all those 25% up. So that's your usefulness of a box plot. Now, the other thing with box plots is they are commonly utilized to discuss information. And you are commonly asked to describe, this is the most common univariate piece of information you'll be asked to describe. You'll be asked to describe box plots in terms of their shape, center, spread, and outliers. So, outliers, are they present? If so, what are they? Also note if there are no outliers. Center, note the mean or the median. You can see that, you can see the median. The median's usually the easiest. I usually always go to the median because you can see the median in a box plot. It's the middle line. You then have your mode as well. So your mode is less easy. You need to have your raw data. Same with the mean. You don't really have to comment on them if you don't have the raw data or you don't have the ability. Usually the median is suffice. The spread, so what is the range of the data from your minimum to your maximum? You don't want to talk in, you want to include your outliers in that. So you want to go your minimum to your maximum. You might also want to talk about your IQR, or if you've been given a standard deviation, we'll talk about that in a second. And then you also want to talk about the shape. Now the shape is a little bit more confusing. The shape looks like this. So if I'll show you some other ones, but this is a histogram. If your histogram looks like this one over here on your left, it means it's positively skewed. It means it tails off into the positive. It's negatively skewed if it tails off into the negative. Now, it doesn't actually need to go into negative values. It just can tail off towards the smaller values. We call this negatively skewed. Approximately symmetrical is the other one. Bimodal has never come up. It was put in their study design a couple of years ago and they removed it, but they never distinctly said you don't need to know it. So we always sort of teach it, even though it's never really come up. So as you can see there, they look a bit like that. Then we have our box plots. Sorry, come back. Then we have our box plots. As you can see here, this is a positively skewed box plot. Sorry, these ones have the correct axes. This is what the numbers on the axis are meant to look like. I do apologize for them getting a bit squished. As you can see here, we have a positively skewed box plot. As you can see on the next one, you've got a negatively skewed box plot. And as I was trying to say, this box plot never goes into the negatives. This doesn't actually, touch the negatives over here. There might be negative values back here, but it never touches it. But it's still negatively skewed because it skews towards the more smaller values. And then as you can see here, we've got approximately symmetrical because this box plot is pretty symmetrical. There's not a lot of difference between them. So that is essentially how you describe the shape of box plots. And then lastly, with numerical data, you need to know normal distribution. I'll touch on this quite briefly, but normal distribution is essentially where your mean equals your median equals your mode. It's used for numerical continuous data, and you have 50% of your data either side of it. So it's like a perfect symmetrical piece of data, and it approaches zero on both ends. Now, normal distribution is really cool because it's utilized for your ATARs. So we normally distribute around a mean median mode of 30. And then we sort of distribute from there, and then scaling is very different to that. Don't worry about scaling. But the best way to describe the spread of data is through one, your mean, and then your standard deviation. So your standard deviation is just a value that is calculated in your calculator, and you don't need to worry how to do that. You just have to do it in your calculator, and you do that through your sheets. Most of the time will actually just be given to you. But in a question, you're told, all right, my mean is 5, my standard deviation is 2. What would it mean? What value would I be if I was 1 standard deviation above the mean? Well, you go 5 plus 2. What if I was 2 standard deviations above? Well, you go 5 plus 2 plus 2. What if I was 1 below? 5 take 2, etc. And the reason we do that is because then we can sort of say what percentage of, if it was a mark, maybe it's a mark from an exam or a SAT, what percentage of your class are you ahead of? If I do a mean and a standard deviation of my class's scores, and let's say it's normally distributed, we normally distribute it, we can say, all right, what percentage of my class am I above? Well, if I'm 1 standard deviation above, I'm above, 50%, so 50% on this side, plus 34, I'm above 84% of my class. If I am 2 standard deviations above, well, 84 plus this 13.5, well, I'm now 97.5% of my class is below me, etc. And what's really important is you need to know these 3 lines and this exact diagram. This exact diagram must be in your summary book, full stop. This whole page needs to be in your summary book. I don't want you to screenshot this exact page and put it in. I want you to have this exact diagram screenshotted in, and then I want you to write out the other parts. Really important, you must have this information in your summary book, found reference. Doesn't matter if you don't want it there, it needs to be there. And why it needs to be there is because you get asked questions like this. A class of 24 students receives their science test results with a mean of 32 and a standard deviation of 2. How many students received a mark between 28 and 32? Well, how do I know how to answer this? Well, I go back to this diagram here. What did it say? It said I had a mean of 32 and a standard deviation of 2. Well, a standard deviation 1 below is 30 and a standard deviation 2 below is 28. So 2 standard deviations below is 28. So I'm going to be somewhere over here in between my purple and my blue. And then on the mean was the other value is going to be just over here. So what I need to do is add these 2 together. So I need to say, all right, I have 34 plus 13.5. So what I'm saying is there is 47.5% of my class between those values. And I was told there was 24 students. Well, then I need to find 47.5% of those students and round to the nearest student, because I'm not going to say I have half a student. Half a student doesn't exist. I need a whole number. So as you can see here, 32 take 28 was 4. 4 divided by 2 was 2. So I have 2 standard deviations under the mean. So I need to add those 2 little areas. 34 plus 13.5, 47.5. So then I multiply that percentage as a decimal by 24. I get 11.4. Cannot have 11.4 students. Because it's less than 0.5, I round down. So I've rounded down to 11 students. Really important that you do that. Please make sure you don't round. Make sure you don't leave your answer as 11.4 students. There's not 11.4 students. You need to use common sense in these questions and say, all right, it's not a point. And then we have our Z-scores. So our Z-scores are essentially a little bit different. So we've done that first question, but then it says Ben achieved a result of 35. What is his standardized score? Well, a standardized score, as you can see here, well, actually this first question we haven't done. This is between 28 and 34. You're welcome to do that yourself. So, but your Z-score is a little bit different. Ben achieved a result of 35. What is your standardized score? Well, a standardized score is essentially your Z-score. So you would put it in this formula here. So your actual score was 35. So my X would be 35. So I'd be putting X equals 35 in my calculator. So that's 35. Then I would go to my X bar. Now, X bar is your mean. So I do 35, take 32. So 3 would go on top. And then I go to my standard deviation. Well, my standard deviation is 2. So I put 2 underneath. So I put 3 over 2 in my calculator. I'm going to get an answer of 1.5. So as you can see here, then you also have this first question, which is an extension of that question we did before. I'm going to give you your time. I want you to have a go at that first question if you want. We're not going to go through it, but you're welcome to pause and have a go. You're back. But as you can see here, the answer to the first question is 81.5, and the answer to the second question is 1.5. So that is what a z-score is. So that is univariate data. We probably spent a little bit more time on it than I wanted to, but the reality is it's the first thing you're going to go through. So make sure that you understand how all of those aspects of univariate data work. Now, in our last sort of 45 minutes, we are going to smash through the first half of bivariate. So we're up to slide 86. There's 124 slides, I believe. I did update it, so I think there's 124. But what you will find is that in the slides that are available in the week that this is out there, or those who are watching on ATAR Notes Plus, they'll still be available there. You'll see that the slides go to about 150 something in the PDF. That's because the last 30 slides I've left after our final slide are covering our seasonalization. Now, we will cover that in the autumn lecture series. However, I wanted to put it there in case people have their SAC before the autumn lecture series and people wanted to go through it. You're welcome to go through it yourself. I'm not going to discuss it with you because I'm not going to do it in this chat or in this sort of lecture, but the slides are there. So you're welcome to look at the slides and have a read through them. They're pretty sort of detailed in terms of they discuss exactly what you need to know. So in that sense, they're pretty good. You don't need to worry about trying to decipher what's going on in them. They're pretty good for that. All right. So univariate data is great at telling us what. So what is the average height of people in this room? What is the most popular color, etc. So that's what univariate data is used for. Bivariate data is great for comparing and answering why. So what is the relationship between age and height? Does gender play a role in someone's favorite color? How do you average temperatures in all major cities compare? So you are comparing two things. So bivariate data, when we've got more than one variable, we give the variables different names. So science kids will know this is the independent and dependent. For general maths, we call this explanatory and response. They are the exact same thing, we just use different naming. Explanatory is known as the independent variable, or in general, we are going to call it explanatory variable EV. This is plotted on the x-axis. The explanatory variable explains what's going on. So this, therefore, causes a change in the response variable. So a good way of thinking about this is height versus age. Well, age is going to be your explanatory variable. Your height does not explain your age, but your age does explain your height. Another example is shoe size. Your shoe size does not explain your age, but your age does explain your shoe size. As you grow up, your shoe size gets bigger. It's not as your shoe size gets bigger, you are growing up. It may not be that. So it's really important to understand that your age is what changes that. So your response variable, which is your RV, or known in science as your dependent variable, but we are going to use RV, not DV. We're going to use RV in general maths, is the variable you think will be changed as a response. So age to shoe size. It's not shoe size to age. So this is another really good summary of the different type of graphs you need to know. So this is a great little summary. It shows you each of the sort of major types of graphs and what the explanatory variable is and what the response variable is. So you've got a explanatory variable of categorical versus response variable of categorical for segmented bar charts or two-way frequency tables. And then we move into things like parallel box plots, which use some numerical, stem and leaf plots back-to-back, which use a bit of numerical. And then we use scatter plots, which are numerical and numerical. Scatter plots are easily the most useful and are what you're going to spend the most time on in further. They are going to be the most challenging thing, but you are going to get pretty used to them, and you are going to sort of end up, most people end up enjoying them because they are difficult, but they do sort of make sense in the end. So we won't spend a lot of time on these graphs. We'll spend a lot of time on scatter plots. So we'll probably it will probably take us 10 minutes. and we're going to blast through the next sort of 10 to 15 slides, and then the last 10 to 15 slides will take us a good 25 minutes to go through. So, as you can see here, we have segmented bar charts. So segmented bar charts are essentially where we compare categorical data with categorical data. Now, because they are segmented and it's bivariate, we use different colors. So you know how before I said in our bar charts for our univariate categorical data, I want you to use one color. In this case here, I want you to use more than one. As you can see, I have the year. So the year is a categorical ordinal because it has an order and it's categorical. And then I have cold, mild, or hot. Once again, categorical ordinal because we have an order. Now, the year is a number, yes, but it describes a time period. Cold, mild, hot describes a temperature. So the number of days at a temperature level. Now we've got a frequency. Now, really important, segmented bar charts usually are required to be in a frequency. Yes, you can, a percentage frequency, sorry. You can do it in just a general frequency, and they'll all be different heights. But the best way to do it is to do a percentage frequency, because then you can directly compare each category. Now, the next point is they need to be in the same order. So you need to have hot at the bottom, mild in the middle, and cold at the top for all three of them. Now, if you wanted to do cold, then hot, then mild, doesn't matter. It just needs to be, each of the three of them needs to have them in the same order. If they're not in the same order, then it's just wrong. Throw it out the door. The other thing is it needs to have color coding for each of the different categories that are in the bar. So as you can see here, this is your explanatory variable. This is your response variable. Your response variables need to have different colors accordingly. So cold here, they've given blue, mild, they've given green, red, hot. Doesn't really matter, the colors sort of match up with it. But nonetheless, the colors need to be the same. So for 2010, 11, and 12, hot needs to be red, and there needs to be a key. Same with mild, needs to be green for each of the three of them. Cold, it needs to be blue for each of the three of them. And notice how, because they're frequency, they're really easy to compare. So percentage frequency, they're really easy to compare. Percentage frequency, they all need to get to 100%, which makes sense. It's 100% data. And then, as you can see, you can sort of compare these directly. You can say, all right, well, this is 100 to, probably like 76. So it's like 24% of the year 2010 was cold. Whereas in 2011, it was like, maybe this is like 87, so it's like 13%. And then here you could say it was maybe like, that's maybe down to like 81, so you could say like 19% in 2012. So it's a really easy way of comparing. It's a really nice way of comparing. And then you go through it like that. So this is a really nice little graph to be able to draw and to be able to utilize, but you really, really need to know that you do need a key. Really important. If you don't have a key, it is wrong. There's no explanation as to what's going on here. Now there is. You need to have a key. Now, two-way frequency tables. Again, these are not all that useful. Now they are, but they're not. Again, we want to avoid frequency tables at all costs. So frequency tables are last resort, just like in univariate, in bivariate, we don't want to use frequency tables. So frequency tables can be two-way in a sense that we have our response variable on our rows, so for and against, and we have our explanatory variable in our columns. So the year level is going to explain the for and against maybe a new policy change at the school. Maybe it's got to do with year 12 jumpers or something. You're obviously going to have more people in the for year 12 because it affects year 12, like they want it, whereas against as year 11s are generally against it because it might be detrimental to them, so they're more likely to be against it. So that's why the year level is explanatory and the attitude is the response. Really important with these graphs. Again, please try and do them as a percentage. You can do them as raw data, but the percentage is better just because you may have different numbers of year 11s and different numbers of year 12, so then your data looks a bit weird because it might look like there might be way more year 12s that answered it than there are year 11s. So then your 19% might actually be as a raw data value like 20, but then your 64% of your 11s might as a raw data be like 18. So then it looks like, you might look at it and be like, oh, there's actually more people against it in the year 12s, but if you look at that as a percentage, it's a lot less. So please try and use percentages rather than raw data. Once again, we always want to use percentages over raw data. So what can we see from this? So then you can discuss where are the associations. If it was random, we would expect percentage to be around 50-50, but it's not. So therefore, we can discuss that there is an association between these things. And that's why, as much as a frequency tables aren't as useful, that they can still display this stuff and be useful in terms of looking at what's going on. So, moving forward, back-to-back stem and leaf plots. So, back-to-back stem and leaf plots can use two pieces of categorical data, and they can use numerical data. So, it's a bit of an odd one here because in this sense here, we might be looking at, I don't know, age or maybe, diameter of the iris or something. It's a bit weird. I don't know why we used eye color and then, I don't know, whatever the numerical piece of data is here. It's a bit of a weird example. I don't know why we use this exact example. But as you can see here, we've got a key that says 1 to 0 equals 10, and then we've got our blue eyes versus our brown eyes. So, bit of an odd example, but essentially let's just say this is age, some weird reason. So we're looking at people that are 100 years old or 58 years old as our lowest. We'll say it's age, and we're looking at the eye color. You can only have two categorical pieces of data here. You can't have more than two. If you've got more than two, you can't use a stem and leaf plot, or a back-to-back stem and leaf plot, as it's called. And then our numerical data is the age. So, they're 58 years old, 61 years old, 60 years old, etc. And we're trying to see if there's association. It's a bit of a weird one, but essentially that's what they're doing there. And then, as you can see here, we also have our parallel dot plots. Now, parallel dot plots, you can have more than two pieces of categorical data. For every piece of categorical data, you've just got to have another dot plot. Key point with dot plots. They must be on the same axis in terms of the numbers must match up. So they're not on the same axis in terms of you draw a line each time you have a category. So you do a line for boys, you do a line for girls, you do a line for, whatever the next one is. Like if you're not using genders in a sense, you could use, say year levels again. So you're year 10, year 11, year 12. You just write a third line up here. So as you can see, you just keep writing a line every time, or drawing out a line each time, and then putting your data on. But the lines need to match up. As you can see here, this could be ages, this could be boys and girls, and then this could be the ages of the boys and girls that are, swimming at a swim club. This could be like a swimming club or something like that. And as you can see here, you've got your boys, you've got your girls, and you've got your ages along this line here. And as you can see, all of the data values match up. So you've got 11, you've got 10, you've got 10. Yes, the actual values are different, like the actual data and the frequency of each, because you're measuring, you've counted in different categories. But your axis lines up, and it's really important your axis has to line up. You cannot have different axes. You can't start this axis at 8 rather than starting this one at 9. And then lastly, probably our most important one outside of our scatter plots is our box plots. And our box plots generally get asked to discuss the differences between them. So comparing box plots, because we always get asked to discuss, box plots in our univariate, they always ask us to discuss box plots in our bivariate. It just happens to be the way things work. They just like to do it like that. And we sort of just have to get used to it. So as you can see here, when we have our box plots here, let's just say this is, in this case here, we've used our boys and our girls, and we're using a score. Maybe it's like a beep test or something. I don't know what it is. Nonetheless, if you're only 26 in a beep test, you've broken the beep test. It's too far. Nonetheless, you've got a boys one's at the top and a girls one's at the top. Now, really important about our parallel box plots, we have one axis. So you can't actually, have different axes and then make that mistake. You have one axis and you just draw them on top of each other. And then you just write to the side which one it is, or label each one. So as you can see, they're all on the same axis. Therefore, you cannot get the axis side of things wrong like you potentially can with a parallel dot plot. In this one here as well, we use categorical and numerical data. Again, numerical data is on that axis and our categorical data is each box plot. So for each category, we have another box plot. You can have as many box plots as you want. That's up to you. You're welcome to do it. A really common thing for people to do with this as well is to put the axis in the middle if you've got two categories. Say put the axis in the middle and they put one box plot below and one box plot above. You're welcome to do that. There's nothing against it. It looks kind of cool. Sometimes it's easier to read. Happy for you to do that. But in this question here, they want you to discuss the exact points we discussed earlier, but they want you to compare it. So as you can see here, this response doesn't give context, and that's why I don't like this response. I think it needs to give context first. So you need to say first, parallel box plots are utilized to display test scores between boys and girls in a class. Full stop. Then we go on to our first. The distribution of boys' scores test scores on the test are negatively skewed, whilst the girls' scores is positively skewed. You've compared the shape. Done. Full stop. There are no outliers. Full stop. I would rather you say there are no outliers in each category. Full stop. Yeah, that works better. The median score for boys is higher. Median equals 23. Then for girls, median equals 9.5. Really, really good. They stated the values. Really important. You shouldn't just say one is higher than the other without stating the values. The IQR is smaller for boys, 10, than for girls. The range for scores for boys and girls is equal. Range equals 19. Really awesome response. Outside of not having the context, this is a great response in terms of that they stated the values whenever they compared. So they always compared. They always said, you know, one is higher than the other, one is higher than the other. Then they said that they are equal, but they gave the value every single time. And that's really, really important. So that's the best way to describe it. You will commonly get asked to describe categorical and numerical bivariate as a box plot, less commonly as a dot plot, because a dot plot is less, it's not as easy to work with, and very, very rarely as a back-to-back stem and leaf. That's also quite difficult to work with. But then we move into bivariate. Bivariate numerical, So we've got numerical versus numerical. Well, in this case here, we use a scatter plot. Now, this is easily the most useful and the most common in real-world examples. It's just so much better to look at numerical versus numerical. You get so much more information out of it, and you can sort of plot this out on your calculator, and it looks a lot like this. Now, when you get a piece of, a piece of bivariate data that is numerical, and you get a dot plot, you're going to be asked three things about it. You're going to be asked, well, what is the strength of the data? What is the direction of the data? And what is the form of the data? And you're going to say to me, what the heck does that mean? So let's go through each of those. First of all, let's talk about strength. Strength of the data is calculated by your Pearson's correlation coefficient. Now, if you didn't do General 1-2, you won't have heard of this before. If you did, this should be a little bit of revision, but this is your R value. Your R value measures the strength of a linear relationship. So what we want to talk about in our scatter plots is how linear is our data? Does our data actually have some sort of linearity to it? And when it's linear, it generally has a trend. We generally assume that a linear relationship is present. In some cases it isn't, but we'll get to that. If there is not a linear relationship present, like your data clearly curves up and then curves down, you should never do an R value. Because if there's a clear curve to it, we assume that the data trends together, but your R value may not say that because there is a curve to it. If your data does not show a distinct curve and it's sort of like a little bit of a mess, you then do an R value, and your R value will be correctly tell you whether there is actually a linear relationship in there or there is not. You always find the R value using your calculator. You cannot do it by hand. You can, but it's technically way too hard, and it's not part of VCAR / VCE. You need to do it on your calculator always. It's in your statistics, or you can do it in your main page if you have the right pieces of information. Now, what's really important is this here. Now, this should be found in your summary book. This is a little summary of how you describe your R value. So you find your R value, you put your data in, or they give you the right information, and you get your R value, and then you need to describe what is the strength. Well, you are going to say that if your R value is between 0.75 and 0.99, or negative 0.75 and negative 0.99, the closer your R value is to 1 or negative 1, the stronger it is. The closer your value is to 0, the weaker it is. So you always want to say if it is between 0.75 and 0.99 or negative 0.75 and negative 0.99, it is a strong linear relationship with your value. And then you can add in this extra bit and you can discuss direction. So direction was one of the other points we wanted to talk about. The R value also gives you direction. If it is a negative value, it is a negative direction. It is going down this way. If it is a positive value, it is going up this way. So that is how you describe direction. So your R value gives you both strength and direction. So super duper important. So you can only calculate R values for linear data sets, which we already discussed. So as you can see here, you got a positive one on the left and you got a negative one on the right. So you can technically say, you know, positive or negative from just looking at it. Your R value gives you more of your strength, but you can do both from your R value. And then you've got your your form. So your form is where you say, okay, I think my data is linear. I think my data is not linear. I think my data doesn't have an association. I think my data is non-linear. So it's very much like strength, but it's where you discuss any of these 4 points. So you need to mention these 4 points in there. And then here's another really nice little summary. Again, I do apologize. I think when I stretched this sort of squeezed up. Some of the pages, when I stretched it, it squeezed, and some of the pages stretched. It was a bit weird. I thought I got through and fixed most of it, but I obviously missed a couple of pages. I do apologize. But nonetheless, this is a really good way of describing sort of your linear data and describing your scatter plots dependent on your R value. So if it's a linear, positive, and strong, it can be concluded the Y value should increase as the X values increase. Linear, positive, moderate, there is some evidence to suggest. Linear, positive, weak, there is limited evidence to suggest. So these are really good ways of describing what's going on with your R value and what's going on with your scatter plot. And it's a great way to put that information into use. All right. Now, in our last 20-ish minutes, we are going to cover bivariate modeling. So as you can see, here's our summary for bivariate. We're going to cover our modeling data. So we're up to page 110. As you can see, these slides are actually not meant to go past 100, but given today we are, and we've only got 124 slides. So we've got 14 slides to go through in our last 20-ish minutes, which is pretty good because that's about how much information there is. So bivariate data, and in particular bivariate data with two numerical values, is extremely useful. This is because we can use it to construct models, mathematical equations that allow us to predict the values of data points we didn't even measure. So, as you can see here with our scatter plot, here clearly shows a trend, and it clearly would have a pretty strong R value. It's positive, and it's a linear form. What if I wanted to predict the value that was out here? What if this x-axis was time, and as you can see, we set 0 maybe as, year 2000, and we're up to at 60, or whatever, however many years we've gone forward. We want to predict what's going to happen in the next couple of years. Well, essentially, we can with this data. If we make a line of best fit and then say, where should our data really be in a couple of years' time? And that is where we can predict and we can model data. So, how do we come up with a line of best fit? So we come up with a line of best fit with the residuals. Now, a line of best fit essentially minimizes, if I draw a line through the data, and then I get the distance between each data point and the line, and I add all of those up, my line of best fit is the line that makes that the smallest number possible. So it makes sure that the sum of all of these residuals here, and we call them residuals. The residual is essentially the distance between the data point and the line of best fit. Make sure the sum of all the residuals in this plot is the smallest possible. Now, that's really hard to do by hand. So essentially, we do it on the calculator, and we come up with these cool equations that give you what you want. So this works best if there's no outliers. If you've got outliers, it's a little bit difficult because therefore you've got to sort of operate around them, and they can get really confusing. So please make sure you try to use data that doesn't have outliers. If it does, therefore it can skew it a little bit. So what does a line of best fit look like? It looks like y equals a plus bx. Now, a lot of you will say, well, that looks a lot like y equals mx plus c. It's exactly the same. There's no other way of putting it. It's exactly the same. However, we put the C at the front and we call it A, and we put the B, we make the M a B. So what that means, you need to have your C, which is your y-axis intercept. Your y-axis intercept, which is C, is now A, and it has to be before your mx or your bx in this case. And then your b, which was your m, which is your gradient, needs to be after it. So we use y equals a plus bx. It's a linear equation. Y is your response variable again, and x is your explanatory variable, just like our axes. So we have our x on our x-axis and our y on our y-axis. Makes sense. And please make sure you're entering these variables in correct order. Classic VCAR trick to give you the y variable before the x variable or the x variable before the y variable, and they confuse you. Please make sure you're putting your values in the right way. Now, there are two ways to calculate this line, and there are two scenarios that you'll be given. First of all, you'll just be given all the raw data. If you're given all the raw data, you chuck it in a sheet in your calculator. So you go to your sheets part of your calculator, and you put it all in your sheets. You go to your sheets and you go, all right, I'm just going to stick it all in my sheets, and I'm going to put it all in there, and I'm going to get my information that I need. Now, the second way of doing this is they give you these weird pieces of information, and they give you your Pearson's correlation coefficient. They give you your standard deviation of your y data set, your standard deviation of your x data set, and then your mean of your x data set and your mean of your y data set. And they say, tell me what the line of best fit is. And you'll be sitting there like, what is going on? Well, the best way to do this is to use these formulae here. So these formulae need to be in your summary book / bound reference. Again, a non-negotiable, they have to be in there. These formula read B equals, so your slope, your gradient, or your M value, if you like things like that, but it's your B is equal to your Pearson's correlation coefficient multiplied by your standard deviation of Y divided by your standard deviation of X. Really important that that is how that works. You do B first. Calculate B, because then you need your B value to find your A value. And your B value, and your A value is equal to your mean of Y take away B multiplied by your mean of X. So you need your B value first, really important. So as you can see here, we have a model of data. We have some raw data given to you. So the best way to go about this, because you've been given raw data, is put in a calculator. You've been given height and weight. Well, you need to figure out which of these is the X and which of these is the Y. Well, I'm going to say right now that my height is probably going to explain my weight more than my weight explains my height. If I'm taller, I'm probably going to weigh a little bit more. It's just naturally what happens. So height as my X value, weight as my Y value. So you need to interpret that. You need to be able to use logical sense to do that. So put this data into my Casio. So I put it into lists or spreadsheets for the one you want to use. And then I find my regression equation. So I go, I put it in and I go, all right, I want linear regression. I do regression. Usually it's in like your settings or your calculations part of your Casio, and you find this exact piece of information here. So you will go through and it will give it to you, and then you put that on the page. Really important, you don't write y equals 58.022 plus 1.63 by x. You put in your variables. You say weight equals 58.022 plus 1.63 multiplied by your height. Now, you also may need to calculate these values. Now, the best way to describe these values. The best way to describe these values is these exact lines here. I used these exact lines in year 12. I was provided them by my teacher. And then I came here to work at ATAR Notes in 2019. And the lines I used were literally like 2 words different. There were like 2 words that were different. And that's all, and they were exactly the same, pretty much. These lines are universal. You need to be able to put these 2 lines on a piece on the exam, on your SACs, and get them marked. Essentially, if I'm asked to describe my y-intercept, if I'm asked to describe A, I say the y-intercept is at, and I get my A value. And if I'm talking about, again, I'm talking about weight and height. So remember that weight was my response variable. So weight was on my y-axis. So my y-intercept is, let's say A is 15. I say 15, and then weight, maybe it's in kilograms, I say is at 15, full stop. This means the y variable, which was weight, is 15 kilograms. So at the start, you don't want to say 15 kilograms. You want to say my y-intercept is at 15. This means the weight, so y variable, this means the weight is 15 kilograms when the x variable, the height, is 0, maybe it's centimeters, 0 centimeters. Now, that doesn't make any sense. Why would I be 15 kilograms if I'm 0 centimeters tall? That piece of information is a bit useless, but they may ask you to interpret that. Then we say the slope. So if we're asked to interpret b, the slope is, maybe it's 1.2, 1.2. This means that the weight increases because 1.2 is positive. If it was negative 1.2, I would say this means that the weight decreases, but we're using positive here. So 1.2 means the weight increases by 1.2 kilograms for every 1 centimeter increase in height, because the 1 centimeter increase in height gives me a 1.2 kilogram increase in weight. So using the word increases when b is positive and decreases when b is negative, replace everything in, well, it's orange, not red, to fit the context of the question. So it's really important that you change everything that's everything here that's a different color, you change that to fit the context of the question. Now, what about your R squared? So you've probably heard of R squared before, undoubtedly. You would have gone through R squared in year 11. But R squared is used when we can reasonably believe there is causation. Now, we didn't go through causation and correlation because that's actually been removed, but we still go through R squared. So R squared tells us the extent to which X caused Y. So you get your R value, your Pearson's correlation coefficient, and you square it. And because you square it, you're going to get a positive value between 0 and between 1. Your value will be between 0 and 1, and it will be a positive value. You will not get a negative value. If you get a negative value, you've done something wrong. Go back and do it again. And you put it into this exact line here. Again, this is where the red was. This is why I said fill in the red to fit the question. But let's say for my weight and my height, I got an R squared value of, let's say, 0.72. 0.72 is my R squared value. I would say the coefficient of determination tells us that 0.72 by 100% will give me 72%. So I get 72% of the variation in the weight. It's explained by the variation in the height. So I fill in the blanks to make my sentence make sense. R squared will always come out of the calculator positive. We can tell if the positive or we can tell if it is truly positive or negative by observing the scatter plot or gradient. So how do we then interpret the reliability of sort of these pieces of information we've looked at? So we make a line of best fit and we interpret it all. But then what we do is we want to use that line of best fit to say, all right, what's going to happen next year? What's going to happen if I grow this many centimeters? What's going to happen then? Well, if I use a whole grouping of data, and let's say we're talking about our weight and our height, and I use, people in my class, and people in my class vary from 150 centimeters to 180 centimeters. And I'm 170 centimeters, and I want to predict if I go to 175 centimeters, I grow by 5 centimeters, what is my weight going to be? So I get my line of best fit, and I put in my X value, or my height, as 175, and I get a weight of, whatever it is. Let's just say 75 kilos or something, or 72 kilos, whatever it is. That there is my prediction. I'm predicting that if I go to that, I should get to 72 kilos. Well, that's according to the data. That there is what we call an interpolation. That is a fairly reliable prediction. Why? Because it's within the data set. My data set I used to make my line of best fit was from 150 to 180. I predicted within that. Now, what if I was that 180? What if I was that final data point and I knew I was going to grow somehow to 185 centimeters? So I now want to use that line of best fit to predict what my weight will be when I'm 185. And let's just say that says I'm going to be 80 kilos. So I go to 185 centimeters, I'm going to be 80 kilos. That there is extrapolation. That is outside my data set. I'm now outside of that 100 I'm outside of that 150 to 180 on my x-axis. I've moved outside of that. I'm at 185. I'm now predicting beyond what I know. Therefore, we call this an unreliable prediction. As much as it is still utilized, and that's what we do. When we have time, we predict using those. We still call it unreliable because it is outside the data set. So it is extrapolation. So therefore, we call that unreliable extrapolation. Now, how can we mathematically check? Now, the next point, and this sort of builds on from what we've just been looking at, how do we then check if my scatter plot is actually truly linear and I can actually use it for a prediction? Well, we talked about residuals earlier and how we want to minimize those residuals. We can actually plot the residuals on a graph. And what we do is we take our actual y value and we take it away from our predicted y value. So we take it away from our line of best fit and we get residuals. And then we plot those on a graph. And they should look something like this. Now, you should be able to get a graph that sits around a lined y, a line to zero graph. So a line to zero graph is a graph that, as you can see here, it's got your standardized residual on your y-axis, and it's got your predicted or your residual sort of values, not your residual value, so your raw x values on your x-axis. And as you can see here, you've got a line through zero. If your residual plot produces a pattern, no matter what it is, it can be a straight line pattern. It could be a straight line that goes here to here. It could be a curve like this one that goes here to here, or a curve that goes like this one to here. If it has a clear pattern, your residual plot, it means that your original raw data was non-linear. It was not linear and you cannot make predictions with it. However, if your residual plot, first of all, if all the lines are on your line of best fit, you'll have a residual plot that is just a straight line along here. It's the only pattern that indicates that you have a linear set of data. However, if your residual plot has no pattern and it is a mess, you have linear data. So it's a bit of a weird one, but if your residual plot has no pattern, think of it as linear. This is more of a niche thing. It doesn't come up all that often, but it does come up. Now, last quick point. This we're only going to cover very quickly, and it would take far longer for you to sort of understand it in its entirety. So we are just going to cover it very, very briefly. The only point I want you to get from this is, one, this diagram here must be on your summary book. It is a non-negotiable. It must be on your summary book. Now, what does this mean? Now, let's say you've done that residual test and you find that your data is non-linear. You go back to your raw data and you think that your data has a little bit, it might be like this one on the top left here. It's got a little, it looks pretty straight, but it's got a little curve this way. It's got a little bit of a curve like that. What we do is we set that data up on this circle and we put it in that top left. And what we say is, well, let's transform our data to make it linear. We want to make predictions. We want to be able to make predictions, but because it's non-linear according to my residual plot, I can't make predictions. How can I make predictions with it? Well, I need to linearize the data. And to linearize the data, I do this. I do one of the three transformations there. I do y squared, log x, or 1 over x. And then you'll say to me, which one do I do? You do all three. You do all three individually. And when you do all three individually, you then calculate your R value for each of those sets of data. So you'll do your raw x versus y squared. You'll do your raw y versus log x, and you'll do your raw y versus 1 over x. You calculate an R value for each of those three sets of data, and the R value that is closest to 1 or -1, whichever one is the strongest R value, is the transformation you choose. It's a little bit of trial and error. It's a little bit annoying, but you have to do it. And it looks something like this. So as you can see here, I've got a raw set of data, y and x, which needed transforming because it was not very linear. So therefore I transformed my x values and I did x squared. And as you can see, it worked pretty well. I obviously got a pretty good R value. So therefore we then can graph it, and you graph it as y versus x squared. And as you can see, this is what that data looked like. So this was pre-transformation, clearly got a bit of a curve. And if I go back to my curve here, I'm going to use my x squared because I'm in my bottom right. So I'm down here in my bottom right. As you can see, down here in my bottom right, I ended up using my x squared. So I go here, I did my x squared, and this was my pre-transformation, and this here was my post-transformation. So as you can see, I got a really high R squared, also means I got a really high R. But the most important thing is when I plotted it, I made sure to note that it has been transformed. It is no longer raw data. It has been transformed. So if this was age down here, let's just say it was age, I'd go bracket age, bracket squared. So I'd say age squared. Y would stay the same. So let's just say, in this case here, we're talking about height or weight or maybe shoe size. I'd say shoe size. Oh, shoe size is a categorical, so I need something that's numerical. Let's just say, we'll say weight. Weight, you'd put Y. So you'd just say weight because that hasn't been transformed. But your age needs to be age squared because it has been transformed. So that is your modeling data. From your modeling data, you should be able to interpret and calculate line of best fits, do your transformations, look at your residual plots, and look at your R squared. What's really important from here is that then the last topic builds upon this and you go through time series. Now, I'm not going to go through time series. There are 30, a little bit less than that, 20-something slides here that are available in the PDF that you will be able to look at, which will be below this video. These slides cover everything else that you need to know. So they cover all of your time series. They cover all of how to manipulate time series. This is just a very fancy way of saying scatter plots with time at the bottom. Nonetheless, that's everything for today. If you have any questions, please utilize the chat in the last minute, or if you're not at the premiere, please make sure you just look through the chat. There will be your questions will probably have already been asked and have probably already been answered. Otherwise, I'll be seeing you throughout the year for all the other general maths lectures. Good luck, and I'll see you then.